so in this section we are going to be looking at solving differential equations. It's section 11.10, it's on page 322, and basically what we are doing is we are going to be seeing how can we use integration to solve differential equations, okay? And we're going to do this by method of separation of variables. So in general, if we have a differential equation that looks a bit like this, where we have dy by dx as a product of two different functions, okay? So one is in terms of x and the other is in terms of y. We can separate out the variables and rewrite it like this. Okay, and integrate, like, solve it. Okay, now what happens is if we do solve this differential equation, we are also going to get a constant, but we only have to include constants on one of the side. Okay, and I preferably like to add my constant on the right hand side of my differential equation. So let's look at a really quick example before I give you a detailed example. So if your differential equation looked a little bit like this, then basically what could it have been if you had gone one step backwards, meaning if you had a function of y in terms of x, what could your function have looked like? It could have looked something like this, couldn't it? Because 12x squared integrates to 4x cubed, 1 integrates to x, and then you would also get a constant. Now this constant could be anything really, and this function could have looked, either it could have looked like this, or it could also have looked something like this. Okay, and the different constants could have an impact on where your function is, or where it's going through the y-axis, and also obviously the x-axis. Okay, so you could have had something like this, or something like this. Okay, depending on what your c is. All right. Now, each of these different constants would then give a particular solution. Now this is something that's called a general solution, and it's called a general solution because we haven't calculated c yet, but there is a way of calculating c. Obviously, if you have values of x corresponding values of y, you can calculate what your constant will be, and that will give you a particular solution. Okay, right, now let's have a look at a full example. Page 323 now. So the question says, find a general solution to the differential equation 1 plus x squared dy by dx equals x tan y. Okay, so as you can see, we've got a variety of different variables here. We've got x's and we've got y's, and we've got to separate them. Okay, and we are going to bring tan y down here. So 1 over tan y dy equals x stays on the right because we want it on the right. 1 plus x squared comes here, and this dx goes there. Basically, we want all the x's with x's and the y's with the y's. And now we can integrate both sides. Now there is another way of writing 1 over tan y, and that is cot y. Okay, and then here we have x over 1 plus x squared, and what we are going to use is to integrate this bit. We are going to be using our reverse chain rule to integrate this, okay, which you've learned in the previous exercises. And I can show you that here, for example. So if you had this function, okay, and you wanted to integrate this, your u would be 1 plus x squared, du by dx would be 2x. So dx would be du over 2x. Put in your substitution. Okay, and this would have given you 1 over 2 ln u, and that gives you half ln 1 plus x squared. Okay, and this is what I'm going to be plugging in here. So I've already integrated it now, so I might as well just put it in, and then I'm going to add on a constant. Okay, separate all of this bit of the working. When you are sitting in an A-level exam, and if you do something like this, what I've just done here, it's absolutely fine. Okay, so sometimes actually advisable to draw a little margin on the right to do all your jottings. Okay, now what do we get if we integrate cot? That should be in your formula booklet, and you get ln sine y, and then I've already got the right hand side integrated. Okay, but I now want to write my answer. Actually, there's one more thing I forgot to mention. If you get an ln on the right hand side, okay, if you integrate one of these functions, you must also write your constant as ln c. Okay, and I'll tell you why now. Okay, so what's going to happen is I am now going to try and simplify this whole answer. Okay, so I can now take one more thing I can do is, because I've got a positive sign here, what that means is I'm multiplying this by this, so I can write this as c 1 plus x squared. Okay, and now I've got ln on both sides, and they can actually get essentially cancelled out, so I'll be left with sine y equals c 1 plus x squared in the square root. Okay, so the reason why I included the ln with my constant is because later on it makes my work really simple. Okay, it doesn't really have any effect on the answer because ln c is a constant, c on its own is also a constant, so it doesn't really have any effect on the final answer. Alright, now we are going to have a look at an example where we find a particular solution. Now this is something that's called a general solution, and that is because we have got this constant that we haven't worked out yet. Okay, so here's the next example, and just remember that we are now going to be finding the particular solution, okay, which only means that whatever we just did in the previous example, we'll do something like that, and then we are going to actually find the value of the constant. Okay, so let's first separate out the variables. So we've got minus, so we'll bring that down, so we'll have minus 1 over 3 y minus 2 dy equals 1 over 2x plus 1 x plus 2 dx. Okay, and what we are going to do is we are now going to separate, well, first of all we're going to have to split this into partial fractions. Actually, what I am tempted to do is to bring this minus 3 over there on the top. Okay, so the left hand side is pretty simple to integrate. We're just going to get ln y minus 2. But the right hand side, we are going to have to use our methods that we used in the partial fractions video. Okay, so let me just repeat this, copy this down, and then do this separately. Okay, so if we had minus 3 over 2x plus 1 x plus 2 I will be splitting this as such. Okay, and then multiply them out. Okay, and then I am going to let x equals minus 2, and when x is equal to minus 2, I will get b equals 1. Then to eliminate 2x plus 1, I'm going to let x equals minus a half, and that will give me a equals minus 2. Okay, and then once we've split that up, I am going to go on the other side of my page now. So now I've got ln y minus 2 equals, and then this splitted up is 1 over x plus 2 minus 2 over 2x plus 1 dx. And then if I integrate that, I am going to get ln x plus 2 minus 2 ln 2x plus 1 divided by 2, because you have to divide by its derivative, plus ln c. Okay, so remember, because I've got ln's in my solution, I also need to have my constant with an ln. That's going to give me ln y minus 2 equals ln x plus 2 minus ln 2x plus 1 plus ln c. Now I'm going to simplify it by doing this, because remember, I want to write this as y equals something. Okay, the question actually asked for this form. Alright, so I will have ln y minus 2 equals ln x plus 2 over, because I've got a minus sign, 2x plus 1, and then this I am going to multiply by my constant, which is c. In the next step, the ln's can get cancelled out, so I'm going to have y minus 2 equals c x plus 2 over 2x plus 1. Okay, so now they're asking for a particular solution. Actually, let's take this minus 2 on the other side. So all I now have to do is substitute the values that they've given. So they've given that when x is 1, y is 4. So let's sub that in. Okay, so I've got 4 equals c plus 2. So c must be equal to 2. And now my final answer is 2 times x plus 2, 2x plus 1 plus 2. Okay, and now I have a particular solution.